enthusiast. That's also possible. Har ni missat vad vi ska göra? Ja, vi hade det missat. Och det här är ju med och vi tar stödra. Quite a full presentation, so we might have to skip a few.
Yeah, I'll be very quick. I think I'll just introduce you.
So I can just write the note on the board and then okay. And I have a notebook here. Okay.
I think there is nobody there, so we can probably start. Yeah, you want to just introduce it? Then I have a couple of slides. Thank you. That might. Okay, the attendance is a bit low compared to the last time, but I think there is also a link that is provided for following it online. And yeah, we are actually live. The stream is going on, and I would like to welcome you for the continued series of the TN webinars. And today we have Stephen. Probably Philip will introduce him better. So yeah. Stephen comes from industry, and then I let all the suspense with Philip and Stephen to talk about. He will be talking about AI. As usual, we will be announcing the next lecture in a week or 10 days about what is the next topic. I will welcome you all for the lecture.
Yeah, thanks everybody to join. I have just a few slides just to introduce Stephen. I will keep it very short because I know that Stephen has prepared more content than I did. So very briefly, this is a project that Stephen is going to work on. It's the title of the project is Secure Multi-Sensor Autonomous Robots and Surveillance Operations for Search and Rescue Operations in Smart Buildings. It's a very long title, but the scope of the project is to develop technologies for rescue people that are potentially trapped into buildings after disaster. So, and the idea here is to combine the technologies from robotics, so building robots that are able to enter these narrow paths that can be as an effect, originated as an effect of a disaster, where other kind of robots cannot go, and bridging this field with the field of smart building. That's why actually this project is a cooperation between our department and the group of the smart research group in Postroom. So the other co-supervisor of Stephen is Nils-Olof Skeie. So he's going to start this journey, trying to bridge the field of autonomous robots with the field of smart buildings. And this is just a scenario that we are dreaming of right now. We are just imagining the possible applications that we can get out of this project. So as you can see, the idea is to use, for instance, snake robots at this stage is as a concept to actually reach people that are potentially still alive or victims, and then basically maybe support them with necessary like water or other kind of vital tools, and also complement these kind of robots with maybe wearable devices that will be then used, for instance, potentially to lead the people outside the building if there is a way to escape the building. Or the idea is also to use snake robots in combination with other kind of robots, for instance, drones, and merging basically the information that might come from different robots and also from the building itself in terms of sensors that might be embedded in the building before the disaster, during the disaster, and after the disaster. So these are the phases that we are going to target. So as I said, I will keep it very short. And just leave the stage to Steven.
Well, welcome again. My name is Steven Bos, and for the next 30 to 40 minutes, I will talk about AI and understanding the world with AI. I tried, when I was creating the seminar, to create one sheet to give you right away a sort of metaphor to think about, maybe during this entire seminar, on what the essence of AI is. So, and I tried to do it a bit mathematical as well. Of course, a system approach. There's an input, there's some processing, and there's an output. But also really showing that AI is just a tool, a framework that we can use to solve a problem. So let's look at the landscape of potential problems. There's a lot of problems out there, and let's say that a problem is a flower. Then there's a lot of flowers. There's a huge variety of flowers, and not all of them are solvable or have interactions with, for example, bees. And sometimes these bees like a flower, sometimes not, and sometimes this bee might not be able to fit on the flower to do. Well, in Dutch it's called kruisbestuiving, like mixing with the flower. And the goal, of course, is then to get some output from that mixing or interaction with the flower, and that is the honey. And at the moment, AI is a sort of a honey. It is a sort of a lure that a lot of people are interested in. And in this talk, I'm going to tell you about what is very alluring on AI, but also about the potential problems there are and the stings you can get when you actually try to solve problems with AI. In a sense, it's just finding a mapping between input and output, and we will see this more during this seminar. Okay, so I hope at the end you're just like a bit inspired to see how AI might help you in your problems, and know about some of the common pitfalls. Have some resources, because there's a lot of resources in this presentation about links, certifications that you can do yourself to get more and deeper into this subject. and hopefully convince you that AI, as it is today already, is able to help you understand the world that is around you, but maybe your own problem domain as well. So maybe a step back, and I'd like to take you through a certain journey, like where I started with it, actually. So it started like when I was 8. I got this computer from my dad. He just brought it home, an X386, and I think in 3 days I broke the computer. So I started with this manual that was attached to it, and this manual was full of commands. And I didn't understand these commands. I just typed them in, and at some point I hit Format C, and then all the OS of the system was gone. So that was my first interaction with technology. It was really, well, interesting, because at that point I learned that you can do a lot with a computer, and you can break it just as easy. I got inspired by my uncles to do some work in IT. So I worked in an IT shop since I was 14, and then was interested in IT enough to go to university and learn more about the subject. But it was not until I did my master's at Delft University that I was really finding my spot and learning that AI is something that I really want to know more about, maybe for the rest of my life. And it was actually that a professor called Leon Roodkrans, who just had like a single sheet, right? It's basically when I was there in Africa, you just this whiteboard, and this single whiteboard, he was able to talk hours and hours over how AI, this was just before like the deep learning movement that is currently going on in AI. He could talk hours about how there's all kinds of problems with AI, and there's all kinds of interesting things that you should know about if you want to apply it. And that was really inspiring, but it was another lecture by Professor Pascal Wiggers on real-time AI that actually posed a question that triggered me to really investigate in this subject. And it was, there's a problem out there that is not solved yet. So like back in the days, you had IBM solving the chess challenge, right? Deep Blue. There was this other problem, huge problem, called the natural language problem. And that's about understanding language. How can a machine learn language? Understand language on a level that you can reason with it, can answer things. And that was actually really interesting, because that was like a trigger, right? So like a red flag. So okay, that's a problem I can focus on. So for like a year, I've been writing on this like literature overview, which should be like a month or so, according to my study program. But I took a year to research and learn more about all these fascinating aspects of language, of AI that is needed for language. And actually, there's a lot of fields that are dealing with this problem. Philosophy of mind, computational linguistics, evolutionary biology, and to actually process this, it was like an endless array of books and papers. And well, this is actually a summary of about 100 pages, where I just picked things that I find interesting to create this sort of computational framework to deal with this problem. And it was actually, maybe I was writing halfway, that there was this big company. Let me see. There was this big company called IBM that basically solved it. They basically solved the comprehension problem. And before I go into this short video on how it did it, and how it actually was able to win against two human players. Let me give you a bit of theory about what understanding is, and hopefully help you understand more about yourself as well in your process of acquiring knowledge. So there's this theory about what language is, and it ought to be a function of communication by an evolutionary biologist called Tomasello, who did a lot of research on primates. And well, because of that, we can use the classical model for communication by Shannon and model it as a sort of a source, a message, and a receiver kind of model. And if you apply that to meaning and understanding, it will become something like this. So you define language as a structured system. You take it, you interpret language as a sort of compression and encoding of a message as bodily primitives. For example, your body is using your sensors all the time. To understand something, you need to hear it, see it, feel it, experience it, like have your heart rate increase to find something interesting. So these bodily primitives are at the base of what experience is. And it is the encoding of a message in these kind of primitives that is essentially meaning. And we'll get to that a bit later. But that meaning is broadcasted in some sort of source, like you're saying it, like your speech organ, that's the transmitter. Your ears are, of course, the receivers. And then there's, of course, all kinds of noise. This room uses air to transmit my message to you, but underwater there might be a lot of, it's another medium, so it's difficult to get an audio signal across. And then there's, of course, the receiving by the interpreter. So you, in this case, if I am the sender. And that's your brain that's working there. Well, I'm not going to discuss too much about what kind of levels you could think of. And I'm not saying this is the truth, but if you're interested in what meaning means and what understanding could be on a sort of philosophical but also practical level, please read this paper. So let's go to this. I'm not sure if we have audio. It should work.
Yeah. So,
wow. And I was thinking, this is it. This is the last Jeopardy game.
This is Jeopardy, the idea challenge.
Here we go.
It's 2.5 minutes.
Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
4-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Watson.
What is chip?
You are right.
We actually took the lead. We were ahead of them, but then started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is cheek?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The double Jeopardy round of the first game, I thought was phenomenal.
Watson on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
You are right, and with that, you move to $36,681.
So I'm just going
The risk
to skip here and just tell you a bit about Watson. So this is this language challenge. So there's a question posed in natural language. So and it's of course obscured. So it's not that you can immediately see, oh, it's a question about this topic, and so I know the answer. You really need to understand what is what the references are to understand what the answer should be. And then you should pose it in a question as an answer. At the same time, you need to be aware of how confident you are in your answer, because you're going to bet virtual money on it, and that will help you get your momentum or strategically place you and combat these competitors of yours. And you have to do this in like a few seconds. So these guys, they're walking and at the same time disconnected from the internet. So it needs to have all the information on that machine and then do a lot of reasoning and come up with a strategy and an answer. And was able to beat these two persons for the first time in 2011, basically solving the comprehension problem. Basically. So let's continue with the presentation. This is the architecture of that framework, and it is really a computational architecture. It uses and exploits the power of a computer. It generates all these hypotheses over here, and then sort of finds proof for these hypotheses, and then along the way creates this possible answers, rank them, and then submits an answer. And that was quite impressive. There's over 100 algorithms being used, so machine learning algorithms being used to do this trick. Because basically it was a trick, because in the end, when it won, it didn't know that it won. It was just, well, it won. And the variation was so bad, as if it had no common sense. It made errors that humans, like children, would never make. But that's because machine learning can come up with answers that are statistically right, but from a semantic point of view, completely wrong. And that's actually a lesson that you will hear throughout this seminar, that AI is really powerful, but you need to have a deep understanding on what you're actually doing. It was a big revolution in application, at least for AI, and at the moment, we just went to IBM a few days ago. Watson is one of their key products, right? So it's being used in all kinds of domains, medical domain, even in the food domain, to invent new kinds of recipes. It's a fantastic product. On a personal note, I discovered that well, it's not bad to dream big, but you need some support and resources to get like to that point as Watson was. And AI was really going to be big in the coming years, because I saw already then that and it was slightly before deep learning, that if you just combine a lot of algorithms, you can solve basically these hard intelligence questions. And AI has, of course, many problems, not really apparent to the public and media. So there was a lot of misconceptions about AI, which I learned throughout the years. So I often thought, wow, I was reading this newspaper and they say they solved this problem. And I thought, well, I basically have to stop doing my research, right? So they solved it. But then if you go deeper and deeper, you actually learn that, well, on the specific case, it's still really, really a novel area to work on. But most importantly, to really understand on the level that we humans do, you need some sort of body. And this is a thesis called the embodiment thesis. So there's a lot of controversy around it, but it says you need a body to actually understand on the same level as we humans do. And for me, that was the moment I got interested in robotics. So, part 2. Now I'm just going to be a bit more broader and talk about AI in general and the algorithms that are out there, and show you other applications of AI. So let's start with that. Of course, you can also view them at home. I just want to show you a few things. We're already here. And we can do parkour with robots. And look, he actually hits his leg. And it stabilizes, right? Mid-air, it gets his foot tangled against that construction, and it still is able to deal with it. I think this is fascinating. This is actually quite recent. This is the state of the art where we now work with. You can learn them. You can play with them. They're not magic. Another one is this one. It's actually from a few years old, but
Hi,
it's still relevant.
my name is Dimi Carwal, and I'm a researcher focusing on visual object tracking. This talk is the result of my PhD thesis, where I investigated how to track an unknown object in a video sequence and how to improve the tracking performance during tracking. We have developed an algorithm which we call Predator. As any other tracker,
Sounds cool,
Predator
right?
estimates the object location and scale changes, but in addition, it learns how the object looks and what is not an object. And using this information, it scans every frame, searching for the object. If the object disappears, and later comes back, we are able to detect it. This combination of tracking, learning, and detection is unique, and therefore opens completely new possibilities for a number of industrial applications. First of them is in human-computer interfaces. Consider you want to make an interface where the user catches and drags something, such as a mouse. So using our system, it's possible to select the object which you want to track by a bounding box, and that's it. Now the system is learning how the gesture looks like in different scales, how it looks in different rotations, and so on. And after a while, you have a pretty reliable system which is acting as a virtual mouse. The nice property is that over time, it's getting better and better. So the user has the flexibility to create his own gesture.
This video is quite interesting. But what I want to mention here is how fast it can learn with so little examples, right? And the applications go wild. I mean, he shows that you can do the same thing on car recognition and track them when they're passing bridges, and so there's a lot of noise there, a lot of uncertainty, but the algorithm is able to learn really fast and analyze all kinds of new data quickly. This one is interesting. It's called, it's using genetic algorithms. And here you just say, look, you can be any configuration, doesn't matter, but your goal is to get across the landscape. And at some point it learns, just like we humans, we were fit, we were optimized for an environment, and eventually get to a point that there is a configuration that will get you across. So it learns how much weight, what kind of configuration, what kind of speed it needs to use. And think about it. It's like if you define your problem well, you can let these machines help you guide you to a solution, and you can see the progress. So that's also quite cool. You can see the progress of how these evolutions get better and better over time. So one of the things I want to close off with is something I'm really proud of. It's just a minute, 30 seconds. It's in Dutch, so but you will see the application in a bit. Years ago, when I created this app for the company I work for, called Genomics, in collaboration with Bartimeus, which is the Institute for the Blind in the Netherlands. And this technology is actually, this phone is able to understand your environment and at the same time provide feedback about it, because it knows where it is. It scans the environment and understands its relative position in that environment. It's called the algorithm is called SLAM, simultaneous localization and mapping. And why this is interesting is that that advanced algorithm can now be put in your smartphone. That algorithm is now put in the HoloLens, where you guide people, dogs, I don't know, robots, with centimeter precision to a location, completely computer vision based, and not without without any markers or beacons or any sort of changes to your environment, and it's really, really powerful. So, for example, I added this app to a robot in last year in December, and connected it to the Lomo robot, and first walked around. Created a route. And it's during a hackathon, a company hackathon actually, so there's already some years involved. And I can see. This is actually in Amsterdam Arena, from Ajax, if you're a sports fan. So it now scanned the environment. I created a route within that environment. And now this robot, this is a Segway Lomo, is able to use the smartphone to accurately, centimeter precise, follow that track. And the application was like, it's a sort of guide dog. So you put a leash on it, and then people, blind people, for example, could follow that robot and not use their cane anymore, because this robot will bump into all the obstacles, and it will make people aware that there's somebody who's visually impaired. So here there's a very tight feedback loop, right? It is sensing the direction it should go to, it's sensing the direction of the robot, and then there's a feedback loop to correct it if there's a mismatch. Of course, for blind people, it's not really useful to hold it. So we created all kinds of devices that you can put it on your chest, so that you don't have to hold it and just walk with your cane. But this is just an example of how AI can really transform the lives of a large group of people. I mean, these people, the blind and visually impaired, they don't go outside because if something changes outside, they don't know where they are. Right? They cannot rely on Google Maps to say, well, now take me home, because well, even Google Maps doesn't know where it is, especially not inside. Although they're starting to explore that space as well. And what's more interesting is that if you're blind, 30 centimeter resolution or 1 meter resolution technology is not enough. Because if I'm at the door, then at a distance of 30 centimeters, I have a 360-degree problem of where the door is. I need to have more resolution. I need to know where that handle is to actually go outside. So that's why it's quite interesting to work in this space. Right, so let's go a bit deeper in the theory. This might shock you a bit, this might scare you a bit, but actually it's not too bad. And you don't have to be a math genius to actually understand AI on a level that you can play with it. For playing with AI, you don't need this. But to actually do something useful with it, you probably need some sort of math background, at least know a bit about probability theory, because that's really important in AI, especially in machine learning. And a bit of linear algebra for optimizing problems, and maybe a bit of calculus. It's good to have like a basic background if you read these papers. Let's skip this and talk about AI and machine learning in a sort of context. So they're not the same, of course, AI and machine learning. AI it's much broader. So if you look at the definitions of AI, I've got this book. I was trained at Delft University to follow like the Bible on AI by Russell Norvig and it's called Russell and Norvig. And actually, to answer what AI is, this guy, this very famous guy, Alan Turing, he sort of circumvented answering the problem because to answer what intelligence is in general is like a really philosophical problem. The book from Russell and Norvig actually starts with a full chapter on how you can interpret intelligence. So let's, instead of defining what intelligence is, create a test to see if something is intelligent or not. And then you get to these problem areas, right? And basically these are a lot of the fields that AI is about today. So there's natural language processing, knowledge representation, so should you fit it into a table or should you fit it into a graph, or automated reasoning, machine learning, of course, is really a big one at the moment. Computer vision, robotics, you need all of them to complete the Turing test. And I'm not going to elaborate a lot about what the Turing test is. You can just look it up yourself. But it's really interesting to see that it's actually really hard to just say answer a simple question about what is intelligence. And if we go specifically on machine learning, there's actually been quite a bit of involvement there in the last, say, 10 years. It started on the left with the simple rule-based systems where there was a direct connection between input and output. You create some sort of program and mapping between them. And at some point you don't create the mapping anymore, but let data learn and find out these mappings. That was the sort of the classical machine learning. And then at some point we got a bit smarter. We got like neural networks, and we started to create these features that might be interesting and sort of helping machine learning algorithms to pick what is interesting to learn. And initially that was done by handpicking them, but nowadays, especially with the deep learning algorithms out there, even the features are being learned. So what kind of features are having interesting information to work with and to create this mapping between input and output. There's a lot of resources on where you can learn more about this. There's just on every image there's a source, and then in the final sheets you have some more. If you look at the feedback in machine learning, there's actually sort of three broad categories where that you can help classify machine learning in. So there's a direct label, a direct connection between input and output, so you know what the output is. So for example, I have a house, and this house has a particular value, and I want to learn sort of the conditions where a house becomes more valuable. Then there could be this database with a lot of these houses, including their value and including their features, and also including what the mapping is between the features and the price of the house, of course. And then you're basically saying this is we know what we want. We have the input, and we just basically want to train a network or an algorithm to find this mapping between my input and my output. And sometimes you can do it semi-supervised, so you assist the algorithm by saying, look, this is a good example, you should add more weight to it. But actually, it's really interesting to do it unsupervised. So actually, there's so much data out there. For example, Google tried this machine learning algorithms on cats. So it doesn't know that it is a cat, but it just provides them with a lot of cats, and then hopefully at some point it will recognize what a cat is. And at some point it works. If you look at the paper, there's some strange results as well. And unsupervised learning is really this class that is the holy grail of AI or of machine learning. And then there's reinforcement learning. So looks a bit similar as to the evolutionary approach. So there's a reward function that you create. So if you do a good action, you get rewarded for it, so that you eventually learn a strategy to go to find your goal, which is a bit different from the other three categories, but it is a type of feedback, and you can do various class tasks with that. So, for example, clustering. You have all these houses from a certain value with a certain feature, and you can cluster them together. Or you could, and then of course it's all about having this new data point. So this data point that you have not seen before, and you want to see if it belongs to cluster A or cluster B. So that's basically clustering. But just as interesting could be regression. So if there might be a pattern, so they have this signal right? Especially with robots, right? This signal and this signal that could be continuing, of course, throughout time, and you want to know what might be the next step. So if this robot is going straight forward, you might say, okay, it's going straight forward. So I know in future points of time that t plus 1 it will be there, t plus 2 will be there. So predict where things are moving to. So regression and is really interesting, an interesting task and a useful task actually as well. Well, this is just a sort of a list of all the algorithms that are currently out there. I mean, there are many, many more, but this is a good overview of how machine learning is actually being applied today. A lot of these networks are state of the art. For example, convolutional neural networks is one of these networks that's really good at learning from images. This is basically the pipeline, and I will skip this. I will just go to the last part because we're running out of time. But if you want to know more about this topic of how machine learning works, please go to Filippo and me and Kiro, and we're more than happy to explain more about it. Training, and this was my master thesis that was actually the application of that conceptual framework. So if you're interested in that, please hit that link.
Maybe you can just show the video just to as a summary of the presentation.
I use the Kinect, which is of course a depth camera, and use the.
I grab the red ball.
So here you are combining.
I push the red ball.
Yeah.
I grab the red cup.
So before I continue, just a bit of information. The algorithm is about creating a better speech recognizer. So it's able to hear what's being said, and it's able to see what's going on. So it knows the objects, it knows the gesture, and it's combining all these features into a new understanding of what's going on. Because in the next step, we will add noise, right? So because it's called the cocktail party problem. If there's a lot of noise, people talk and chat, and it becomes really noisy so that you cannot really understand what's being said. You rely on your eyes to see what's happening. So if someone is saying, here's a beer, and you just hear something like beer, you understand by seeing it, okay, so that person is giving me a beer. And basically this was an experiment to replicate that. And on the top you see what's being heard by the speech recognizer, and then in the white you see the deep neural network fusing all these modalities. So at this point, we cannot even understand it anymore. But it is able to, by training enough and enough, understand these minute differences in the audio signal. But for me, this gave me a new focus, because I understood that if you want to do something and really understand something, you have to do a lot of interaction with it. You have to play with it. You have to work with it. And visualization is key, right? So if you have a lot of data, it's just data. But if you write a tool to visualize that data and to see what's actually going on, you better understand it. And then it becomes much more easy to apply an algorithm like a machine learning algorithm. So the final part, like we're going to rush through this, is just saying that AI is, yes, it's good, but as you see on these images here, on the top right of this quadrant, the deep neural network thinks it's the cheetah, and on the right, on the bottom right, it thinks it's a peacock. So if you put on the right inputs, it will create an output anyway. So it is garbage in, garbage out. So you have to be careful. You have to understand what your input data is. Otherwise, you will get bogus data. And the same thing holds for the process. It's actually working in machine learning is 80% of the time you're working with data, understanding your problem domain, doing extractions, filtering, cleaning, transformations. And only 20% you're busy applying that algorithm and getting results. There are a lot of pitfalls, and just listed here. But the most important thing is, of course, data. You need a lot of data in general. There's also good research going on to have little data to train on. But in general, you need a lot of data, and it needs to be of high quality. There's some trends within machine learning going on. Gamification, like using game engines to sort of simulate inputs so that you can create data yourself without having data.
Okay, now, so you create the data after you. How can?
For example, you have this car driving in a simulation, right? And now I can just add trees to it and help it have more scenarios where trees are in it, right? So you place virtual trees, so you don't have to drive your physical car to a forest.
But then it will be a validating problem later on. It doesn't matter. We are at the start.
Right. But we're getting there to a photorealistic version of the world, digitally, right? So for the last 5 years, I'm not going to talk about it. I've been creating digital twins of creating realistic worlds using geodata. So we're starting to get these photorealistic versions of our world that we can play in and train on. Let's have a discussion afterwards. There's these resources that you can look for. A lot of interesting speakers. These podcasts are awesome. This Lex Friedman is an MIT professor that is really interesting to follow. A lot of research going on. If you just look at OpenAI, there's this course. If you just want to prove on your resume that you're doing something with AI, just go to Coursera or edX in this case and apply it for a free course. And if you want to get certified, it's only €100. And you can do this in a week. And my final thoughts is these two inspirational media. So a book about robots that actually face all kinds of problems, but because they're not really human beings. So they try to be human beings, and they get into all kinds of situations. And then there's Alita, which is a fantastic manga actually, especially on the philosophical part, which is out now in the cinema. So if you want to know more about what AI is about, please read and watch these two great movies and books. That's it.
Thank you, Steven. Just also not for talking, but also tells us that the academic work can also be applied in the industry. It doesn't end up in here. But then we have a few more minutes for some questions. I know that there was already one question which we started.
So it's not a question. I always remember every time I want to hit artificial intelligence, I remember that we are just at the start. Right. So I don't do much when I sort of swallow it and say, okay, you're right. I don't want to be taken as skeptical. So it'll be interesting to see how it will develop.
Yeah.
Because what you said is that you need to understand. You said that I need to understand it first.
Yeah. Yeah.
So and then I will teach it somewhere to somebody, and he will evolve in a way that he will be better system to understand the thing that I implemented in him to understand in the first place. Is this what we are doing?
I can follow up on this. Like, for instance, the state of the art, the robot that was doing parkour, right? Jumping the obstacles. So I think that is a very good perspective of what we are now, because that is achievable only if you bridge two main fields. Like the traditional control theory, it's bridged with the current state-of-the-art AI algorithms. It's only feasible if you if you are applying a traditional approach combined with the new algorithms. And I think it's also a good approach to look at scientists working with AI as artisans of data, right? So this is currently in my opinion, at least, the state of the art. But it's
you don't misunderstand me. I totally believe it.
Yeah, no, I saw the point.
I'm trying to understand it also from the perspective of an applicant score. Just as a human, I'm not a scientist, and I'm not. And this is the criticism that you will always hear from the public, is that logic-wise, I need to assure those people that I am the one who's perceiving, and I'm understanding the phenomena first.
From an ethical point of view, right?
From whatever analytical, and even much more than that, because it's multidisciplinary. It's even, I mean, he doesn't know how to be cool. My son, he doesn't need to make this one, but he can prove to me that he's cool and backward, although he doesn't know except two movements. And he can show the people, and that is a high way of intelligence that I don't see that we will reach in the track that we are going. Although you are talking about multidisciplinary, I'm talking about combining many approaches, but I don't see those skills yet in the way that we are approaching the problem. So I believe that even artificial intelligence would have to go like all other sciences, but we mechanical engineering, is that you will have to destroy everything that you do with artificial intelligence today and start from scratch after you have learned actually all the problems that you're hitting. And from a system perspective that I adapted, I know that you have to start from scratch in 5-6 years from now. You have to look for totally different, very new innovative, because we cannot continue like this. It has a problem in itself. The way we approach the problem, and as we say, the B, it has already a bug. And this bug is that it has to go through us, and we are the bug. So we need to find a chain, or a place, or a ledge where we eliminate this. And I don't know how we're going to do it. If you find it, you will manage to decode the message that you're talking about in communication much faster than we are doing now. Because we cannot go with this pace.
I like this combination of stuff that we went through
Yeah, but you do understand what I mean, that we cannot go with this pace because now we are developing in a very slow pace than what we are promising.
Well, people do disagree. I mean, there's especially in the last maybe 5 years, there's been rapid progress on analyzing big amount of data. And if you look at Go, for example, this game that is really difficult to comprehend, even for human players, this machine was able to play Go, learn Go, and beat the best player. And we're finding all these challenges, right? All these tasks that we think is intelligent.
And it was the machine was playing in a way that was like human-like, not cheating or skipping things. Or
it was like playing against another version of itself, right? So it was just competing against itself, but on a way that it became so good that it was able to best the best player. And you see this this search for hard problems, right? So chess was a hard problem that we solved in the 80s. Then there was this comprehension problem, very difficult. Then you see that with Dota and World of Warcraft, and there's all kinds of games that you think that, well, you have to be really strategic to understand the limitations of a unit, but these machines are able to understand that. And you're right that if you think about that they don't have any human like features, right? So they don't feel anything, or they
sentiment,
don't,
or some kind of sentiment, or some
right.
kind of.
So they have these kind of traits, but they are really good at. Well, if it ever hits the solution space with two valid answers, as a programmer, you've thought about that, right? So it will choose either the first solution that it got, if it's the same quality, or it will choose a random one if there's two valid answers. If you add like what Filippo's called like sentiment, and like if you really want to have sort of a weight of what it could mean if I choose this solution and what for kind of effects it could have on other people, that would be a better, of course.
There are actually some new trends that are looking at this, but I think this we are still far away from that. But like introducing sentiment as a form of randomness, for instance, or an approximation of that, of what you think. It is. There are people looking at this now. And also from an ethical perspective, for instance, if you think of the Tesla founder, right? He started recently a new startup that with the goal of augmenting humans with AI, because he said in 10 years from now, machines in some fields, in some specific fields, machines will be better than humans. So it is actually the other way around, right? I think at this stage where we need to look at the other way around, how we can augment humans with sentiment through machines, not machines becoming humans, right? I think at this stage we're currently looking at this perspective, how we can use machines to make humans slightly better or give a chance to compete with machines.
Just want to add one thing. This category we talked about is reinforcement learning. That deals with this sort of sentiment, right? So you can get a reward for choosing a solution that is maybe better for the rest of the society, right? So this is a field of within machine learning that is becoming increasingly popular.
You just mentioned reward, and that was my question. How do you define reward for a machine? I mean, it's easy for a human to introduce dopamine and serotonin, which makes us feel good, and drives us to stuff.
Yeah.
But machine, they don't have feelings, emotions, how do you
So you have to find some sort of measure of purpose, right? So for example, to get to a goal in the shortest amount of time, that could be a bonus, right? That could give you a reward if you get there really fast. Or if you hit as many obstacles, for example, the snake robot that we were trying to train, we wanted to find obstacles to propel against. So it should find a reward for actually hitting these.
So reward is actually a term that is used according to the model, the mathematical model that you built. You can, for instance, use a weight, a parameter that you use as a reward from a logical perspective, not like a reward that you, like a candy that I give to a kid, you know? Yeah. Yeah, I think the term is.
You tell them that the reward is a point.
It's like a score, for instance,
so
right?
He looks to it score. He looks to it as a candy,
Mm.
but he doesn't need to taste the candy. But he understands much better. If you get much, it's better.
Hmm.
Is that the link for this? Yeah, it is. Yeah.
Very interesting.
So you also see the link, just to wrap out, the link of all these methods that Stephen has presented with the project that I very briefly mentioned initially. So there we are also considering to apply AI for several tasks. Is locomotion of the robot. And for instance, using the same algorithm, the SLAM algorithm that you saw in the video with the blinds, with the blind people, right? Could be used there. And we also have some other students like Tuan. Tuan is working on the locomotion as well. And basically, yes, so far developed the low-level controller, meaning that you still need an interface with the machine when you need to control servo motors, sensors, and so on. So he has developed this part, which is the bottom layer, on which Stephen is going to add, together Tuan, they are going to add some smarter algorithms. So that's the overall goal.
So if you make an illusion, it's not making an illusion.
There are hybrid algorithms where you could, for instance, use a simulation environment to pre-learn something or learn enough so that then you can test the robot in a real environment. So you have a pre-learning phase, right? Built on synthetic data, and then you can either continue your learning in a real life, or these hybrid algorithms are starting to appear, right? So that's also a way to combine like the visual world with the real world, right?
Okay, if there are no more questions, you know where Steven is sitting. He's sitting on the 5th floor in the glass vita. So just knock on the door.
How many days? Are you full time?
He's full time. He's full time PhD student. He'll be here for the next 4 years.
Yep.
So just feel free to come and talk to him when you have any questions. Okay. Let's thank the speaker once again.
Interesting.
Good.
Interesting that you're Dutch in the first place. Dutch.